equal to. Okay. So we've got the limit as x approaches negative infinity of x times e to the x. Sure. So there are a couple of different ways that we can approach this, but the first thing that I'm going to do with any limit problem is to just plug the number in. But if I plug the number in, I'm going to have negative infinity times e to the negative infinity. Now, a couple of things to point out. E to the negative infinity is 0. Why is it 0? Because if I think about what a graph of e to the x looks like, as x approaches negative infinity, the y value for e to the x approaches 0. So essentially, this is an infinity times 0 case, which is an indeterminate form, but it's not one that I can apply L'Hopital's to. And because it's not one that I can apply L'Hopital's to, I have to do something to make it infinity over infinity or 0 over 0. And that's where I'm saying we have a couple of options for how to deal with that. One option is to steal the minus sign and to instead say this limit would be the same as taking the limit as x approaches positive infinity of negative x times e to the negative x. And by doing that, I can take the e to the negative x and rewrite that to say the limit as x approaches positive infinity of negative x divided by e to the x. Now, if I plug in infinity, the top is headed to negative infinity, the bottom is headed to positive infinity, and now we're in a format that we can use L'Hopital's. Doesn't matter. So if I've got infinity over infinity, regardless of whether they're positive or negative, I can apply L'Hopital's. Yeah. Not from my practice test. Yeah. So now that I can apply L'Hopital's, yep.
You just change the sign right to get the addition, or is there anything else?
Nope. All I did was change the sign. Yep. Now I can take the derivative of the top and get -1. I can take the derivative of the bottom. It's still e to the x, but now I have -1 over infinity, and this is definitely going to 0, which is the answer to the limit. I think this is the most straightforward path through the problem. Yeah.
Is L'Hopital derivative of the top, or is it both?
It's both, but the derivative of e to the x is e to the x. Yeah. And that one came from Martinez's practice test.
On your test, can we do the number 3?
Yeah. So number 3, I've given us this Gompertz growth model, which is one of the models in the book. And I've told us that our lambda is going to be 2 and that our b value is 0.5. And so 1 minus 0.5 is 0.5. And we can write that as 0.5, or we can write that as 1/2, whatever you prefer. So part A, I've asked if a sub 0 is equal to 4. Well, we want to find a sub 1, and I want to find A after 100 iterations. That does not mean you're going to sit there and do 100 iterations. Something nice should happen on the first iteration. So if I start with 4 and I plug 4 in, then I have 2 times 4 to the 0.5, which maybe is hard to recognize like that, but that's 2 times 4 to the 1/2 power, or 2 times the square root of 4. Since the square root of 4 is 2 and 2 times 2 is 4, this means we put in 4 and we got out 4. So if I were to find A sub 2, it would also end up being 4. So this is 4, and I don't have to do any more work. We're stuck there. That actually is one of our equilibria or steady states or fixed points. B asked us to find all of the fixed points. And again, the book uses fixed points, equilibria, and steady states. And so different instructors, you may have heard different terms. But to find all of the fixed points, that means that I'm saying to be a fixed point or to be at equilibrium, if that's where I am right now, I'm going to remain at the same value for the next iteration. So I replace both A sub n and A sub n plus 1 with A, and then do algebra. So I would have A is equal to 2 times the square root of A, replacing both the A sub n term and the A sub n plus 1 term. Now I'm doing algebra, so I would square both sides. A squared is equal to 4A. And then I can move the 4A over and have A squared minus 4A is equal to 0, which means we have 2 possible solutions. That A is 0 or that A is 4. Now, I've asked to use the stability criterion to classify these. I don't think Martinez got there. But if you're in Chalonor's class, you definitely need to be able to use the stability criterion, which says that I'm going to take that original recursion and think about that as saying f of x is equal to 2 square root of x. And the stability criterion says we're going to take the derivative. And maybe I want to write that as 2x to the 1/2 power. So that when I take the derivative, 1/2 is coming down. 2 times 1/2 is 1. So I'm left with x to the negative 1/2, or 1 over the square root of x. And what we're testing in the stability criterion is what happens when I plug in each of those fixed points. Now, this is undefined at 0. So the stability criterion actually fails for 0, but it doesn't for our other fixed point. We've got a 4. If I put that in as 1 over the square root of 4, that's 1/2. And what we're testing is the absolute value of 1/2 less than 1? Because it is, I know that A equals 4 is stable. Just as another, if anyone would like to see me do that with cobwebbing, I can. Yeah.
Wait, how did you know that that's about 1/2 is less than 1?
So the stability criterion, are you in Chalonor's class? Yeah. So the stability criterion says that we need the slope at the fixed point to be less than 1 in order to be stable. So I know it's a stable equilibrium. If this is greater than 1, then we say that it's unstable.
If that was like 2, then you would say that it would be unstable.
Correct. Yep. I know this was like the very last thing you all went over, so.
Yeah.
What are we doing next? Which one did you want? Oh, I got one in from the back too. Okay. Or this one? Okay. After this, I'll go back and do number 1 from my test. Yeah, okay. So we've got f of x is equal to e to the negative x plus e to the negative 3x. And basically we have to do all the things. So find where it's increasing, decreasing, local max and min, concave up, concave down, sketch the graph. We're doing all the things. So if we're doing all the things on this, and I have to sketch a graph, you know me, I'm looking for partial credit, so I'm going to take the easy things first. Here are the easy things that I see. I can find f of 0. That I can do. E to the 0 plus e to the 0 is 2. Got a point to put on my graph now. More potentially easy things. I can try looking for x-intercepts. I can set the whole thing equal to 0. Fun fact, that's never going to be equal to 0. Because no matter what I put in there for an exponential, e to the something, if I think about just a regular old graph of e to the x, it's always positive. No matter what I put in. And if I want to think about a graph of e to the negative x, it just flips this around, but it's still always positive. So that is never equal to 0, and there are no x-intercepts. So now I guess we have to do the calculus part. So if we're going to do the calculus part, I need a derivative. And when I take that derivative, I'm just going to have to remember to do chain rule. So if I take the derivative of e to the negative x, I would get e to the negative x times negative 1. And if I take the derivative of e to the negative 3x, I would get e to the negative 3x times negative 3. If we're going to find maxes and mins and look where it's increasing and decreasing, I need to set this equal to 0. And do some algebra. Now, there are lots of options for how to do this algebra. I'm going to pick the way I'm going to pick something, and if you don't like it, we'll try something else. When I see e to the negative 3x, I'm really thinking about that as a fraction. I'm thinking about that e to the 3x being in the denominator. And I'm thinking about that e to the negative x as like a 1 over e to the x. So I would probably choose to make this fractions and call that negative 1 over e to the x minus 3 over e to the 3x. If I'm going to set that equal to 0, I really need to get a common denominator there. And this is the part where our exponential rules are coming into play. So my common denominator is e to the 3x. But to get to e to the 3x, I'm going to multiply by e to the 2x over e to the 2x. Because when I multiply those two together, I would add the exponents. So now I've got negative e to the 2x minus 3 all over e to the 3x. Well, if that's going to be equal to 0, I know that e to the 3x is never, oh, question? Yeah.
What did you get the e to, the common, is that the common denominator?
It's the common denominator. Yep. I'm going to set that equal to 0. E to the 3x is never equal to 0, but the top could be. So if I want to look for where the top might be equal to 0, I'm going to have e to the negative 2x minus 3 is equal to 0, which means negative 3 is equal to e to the 2x. And I'm stuck because e to the 2x is never going to be equal to a negative number. So unless I wrote the problem down incorrectly, I do not have relative max or mins because there isn't anywhere where this is equal to 0.
But we don't, like, we disregard the denominator?
Well, is e to the 3x equal to 0?
No, but like, in F.
Oh, in general, no. In general, I need to pay attention to both the numerator and the denominator. It's just for the critical values or the critical numbers, for the things that are breaking up our number line or breaking up where we're doing our intervals. The e to the 3x is never equal to 0. So this thing has no relative maxes or mins. So really the only thing I can say is that it's decreasing because this should always be a negative number on top. So this is decreasing negative infinity to positive infinity. There are no relative maxes or mins. But it also asks us about concavity. So we can check about concavity. So I'm going to go back to that first derivative, which was e to the negative e to the negative x minus 3e to the negative x. Thank you. So if I take a second derivative, I'm going to have another negative pop out. So that'll be e to the negative x. I'll have another negative 3. So that'll be plus 9 e to the negative 3x. And I could do some algebra, but already I know that e to the negative x is always a positive number and e to the negative 3x is always a positive number. So it doesn't matter what I try to plug in. This is always positive. So this is concave up on negative infinity to positive infinity. So the last part of this asks us to graph it. And based on what we have going on here, this graph, I know, passes through the point 0, 2. I know it's decreasing everywhere and concave up everywhere. So it's kind of just going to look like, okay, I missed. we'll just make the circle bigger. It's kind of gonna look like that. It's gotta be decreasing and concave up everywhere. Now, we were not asked in the problem to find that horizontal asymptote, but if I were graphing it and trying to be complete about it, I probably would find that horizontal asymptote, even if I wasn't asked for it. The thing is, both pieces of this go to 0. So my horizontal asymptote out here is just 0. Yeah.
How'd you know 0, 2?
Because I plugged in 0.
Oh, right.
That was the first thing I did. Because again, it didn't explicitly ask for the X and Y intercepts, but I'm going to take some partial credit and find the X and Y intercepts if there are any. Yeah. Yeah. Oh, I know it's decreasing because it's always negative. My derivative is always negative. So if I look at this version of the derivative, e to the something is always greater than 0. So essentially this is like some negative number minus 3. Well, it's definitely negative. And the bottom is a positive number. So a negative over a positive, it's negative everywhere. Okay,
Where the graph is continuous,
everywhere.
including the 0?
Like including at 0 too.
No.
So when you get asked for continuity, we're never talking about the Y values. So when you get asked for continuity, we're talking about the X values. And this is continuous. It keeps going forever to the left and it keeps going forever to the right. Only 3 things can ever happen for the domain. Can't take the square root of 0. Sorry, I can take the square root of 0. I'm like, it's final speak. I can't take the square root of a negative. I can't divide by 0. And I can't take the natural log of 0 or a negative number. We don't have any of that going on in this problem. So the domain is negative infinity to positive infinity, and there are no continuity issues. There also are no differentiability issues because there's nothing that makes this denominator undefined. Okay, so that would do number 1 on my practice next. So let's look at number 1. Oh yeah. It's like I don't even see a sharpener, but if you see it, go for it.
Oh, it's not? What's it take?
I don't know.
That one. It was this one.
Oh. Yeah, no, I was like, no idea. There's a random pen up here if you want to write a pen. Okay, so question 1 from my problems is really like 5 problems in 1, but x cubed minus x minus 1. So if we're going to find the relative minimum of f, whether it's a relative max or a relative min, either way, I need to take that derivative, set equal to 0, either got my number line or my sign chart going. So I've got 3x squared minus 1 when I take the derivative. And if I set that equal to 0, I might write that as 3x squared is equal to 1. So x squared is 1/3, which means, don't forget, x is equal to plus or minus 1 over the square root of 3. So my number line here would need to have both a negative 1 over the square root of 3 and a positive 1 over the square root of 3. So if I'm thinking about test points, I would probably choose 0, 1, and -1. And I'm plugging each of those into my first derivative. So if I plug in 0 into the derivative, I've got 0 minus 1. Well, that's negative. If I plug in a positive 1, then I've got 3 times 1 minus 1, that's positive. And if I plug in a negative 1, don't forget I'm squaring it first. So negative 1 squared becomes positive. And then I've got 3 minus 1, which is positive, which tells me that my function is going up and then down and then back up. And that also means that I've got a relative maximum when x is negative 1 over root 3 and a relative minimum when x is 1 over root 3. To be careful about the question the way I have asked it, I've asked for the relative minimum value of f, not the x. So the relative minimum value of f is, and I'm taking that and plugging it into the original function. So it occurs when x is 1 over root 3, but it's actually f of 1 over root 3. You don't need to simplify this. You just need to show that you plugged it in. Same for that relative max. Our relative maximum value of f is f of negative 1 over root 3. So I'd have negative 1 over root 3 squared minus negative 1 over root 3 minus 1. Yeah.
So, when you get like x, you have to plug it into the original or the derivative?
So that entirely depends on the way the question is asked. So my question asked us for the relative minimum value of f. So that's why I'm plugging it back into f. In terms of like, how do you actually find the x values? You're going to find those x values by using the first derivative. And so when you're doing those test points are going into the first derivative. But to report the final answer, just be careful about how the question is phrased. It might be enough to just give the x values, right? And say there's a relative minimum when x equals positive 1 over root 3. But if the question asks for the value of the function, just make sure you give the value of the function. Part C, find a positive integer nearest to the solution of x cubed minus x minus 1 equals 0. So I don't know whether Martinez had you all do the intermediate value theorem. Cool. So if you wanted to, we could show that there is a solution by using the intermediate value theorem to show that there is at least one solution to this. I didn't ask us to do that in this question. I just asked us to find the integer, the positive integer nearest the solution. So couple options. We know where the relative max and min are, which means we kind of can do a quick sketch. I know that I know it's a cubic. And I know that we've got these relative maxes and mins happening. So 1 over root 3 is a relative minimum. And negative 1 over root 3 is a relative max. So whatever else this thing is doing, I know there's a solution somewhere out there. And because I said that it had to be an integer, we're just going to plug in integers. So if I plug in 1, I would have 1 cubed minus 1 minus 1. So that's -1. So I'll move to the next integer. 2 cubed minus 2 minus 1. That's 8 minus 3. So that would give me a 5. Which of those is closer to 0? Right? So x equals 1 is the closest positive integer solution. And if we were going to use the intermediate value theorem, I would use 1 and 2 as my like my A and B from the intermediate value theorem. And I know that between 1 and 2, my function is only ever increasing. So I also can show that there's exactly one solution. None of that was part of the question I asked. The answer to my question is just the x equals 1.
So basically we're finding y value closer to 0.
Right. Now, the reason we need that is because for part D, I asked us to do Newton's method. So Challenor did get to Newton's method, but I know that Martinez did not.
Over it, but side, I guess.
Yeah. So I guess my question is, does anyone want to see me do Newton's method? Yeah? Okay. I got a request, so we'll do a Newton's method from hello. So does anyone know the formula that we need to use if we're doing Newton's method? Are all of you in Martinez's class?
Yeah.
You sure you want to do Newton's method? I really don't think it's on the final.
Yeah, it's not. It said the linear.
So let's skip it and do part E, and we'll skip D for now. So if I look at E, then that linear approximation at A equals 1. So I know that really the linear approximation is just coming from finding the equation of the tangent line. We just write it in its fancier form. We write it in our fancier form by moving that y1 over and saying we're going to get that by doing f of a. I'm going to find the slope by doing f prime of a. And then I'm going to have x minus a. And we want a to be equal to 1. Well, f of 1, we just found. The derivative at 1, well, we already took the derivative previously. So I'm just going to plug 1 into my derivative. So I'll have 3 minus 2. Sorry, 3 minus 1 is 2. So I'll have 2 for my slope. And then x minus 1. And that's it. That's my linearization. What's next?
Please do this.
I'll do that after I do
Sure.
this one. Yeah.
No, I just have to.
Oh, a question about this one?
Not that one.
Yeah.
I feel like, cause like in the homework, they would like ask for like an actual answer, so I get confused by like here, we're just leaving it as an equation, but like in the homework, it would be like, I don't know, find the linear approximation of 4.9 to the power of 3.
Sure, sure. So if you are asked to use a linearization like to approximate a value, then in general, our equation for the linear approximation, right? We've got f of a plus f prime of a times x minus a. A is the nice number. X is the ugly number. So if I were asked to find the natural log of 1.02, well, my nice number is 1, and the ugly number might be 1.02, and my function would be ln of x. If I was asked to approximate the cube root of 9, what's my function? So my nice number is 8, and my not nice number is 9. Why is 8 the nice number? Yeah. If I was asked to find sine of 0.04, my function is sine of x. My nice number is 0, and my ugly number is 0.04. Yeah. So kind of the process is the same. It's just a matter of, do you have to identify the nice number and the ugly number on your own?
And you got -1 from plugging 1 into the original.
Correct. Yeah. And we had already done that in a different part of the problem, so.
Could you please do the middle problem that you have?
This one?
Yeah.
Sure. So I would choose to rewrite that to say x to the 1/3 to take my derivative. So f prime would be 1/3 x to the -2/3. So f prime of 8 would look like 1/3 of 8 to the -2/3. I'm going to do that in 3 steps. The cube root of 8 is 2. 2 squared is 4. And 4 to the -1 is 1/4. So this is 1/12. So my linear approximation, or my linearization, would look like, well, when I plug in 8, we get 2 plus 1/12 of x minus 8. And I can say that the cube root of 9 is approximately 2 plus 1/12 of 9 minus 8. Okay. And then which one on here were you asking about? The rational function or e to the x times sine of x?
Let's do number 1.
Okay. So again, we're doing all the things, the intercept. Oh, yep. Doing all the things, the intercepts, the asymptotes, increasing, decreasing, concave up, concave to all the things. Sketch the graph. Okay.
I'm sorry, number 1 on where?
This is problem 14.
On yours?
No.
Oh,
So f of x. X minus 1 over x squared plus 9. I don't think, did it ask us for the asymptotes? I'm gonna find them anyway because I need them to graph.
No.
Cool. He's not asking y'all for the asymptotes, but I don't know how to graph it if I don't do them. So I'm gonna look for the asymptotes even when he doesn't ask me to. But easy stuff first, x and y intercepts. Y-intercepts always happen the same way. We're plugging in 0 for x. So f of 0 looks like 0 minus 1 over 0 squared plus 9, and I get -1/9. X-intercepts always happen the same way. We set y equal to 0. And if I set this equal to 0, oops, 9, it can only actually be equal to 0 if the top is 0. So I know that 0 is equal to x minus 1, and x has to be equal to 1.
So for the x-intercepts, we ignore the denominator, but
Correct.
to find the critical numbers, we
So the thing is, I'm not really gonna ignore the denominator. It's just that the denominator is gonna tell me my vertical asymptotes, not my x-intercepts. So I'm still gonna check the denominator. So I'm gonna check for vertical asymptotes by setting the denominator equal to 0. But this is never equal to 0 because that would say the x squared was -9, and that can't happen. So I do not have vertical asymptotes. That doesn't mean I don't have a horizontal asymptote. And horizontal asymptotes, we find the same way no matter what the function is. I'm looking at the limit as x approaches plus or minus infinity. Most of the time it's the same. It's not the same if I have square roots or e to the x, right? Because e to the x goes to 0 in one direction and infinity in the other direction. And if you have square roots, we can end up with two different horizontal asymptotes. Here, nothing interesting is happening. I just have a rational function. If I plug it in, I get infinity over infinity. So we can use L'Hopital's. Derivative of the top is 1, derivative of the bottom is 2x, and that limit is going to 0. So things I know so far, I'm going to go ahead and put on the graph. I've got a horizontal asymptote of 0, a an x-intercept of 1, and a y-intercept of -1/9. That's almost enough information for me to graph this. What I don't know is which side my relative minimum is going to end up on. So I'll do a little bit more work to figure out which side my relative minimum is going to end up on. But at this point, I know it either looks like this or like this. That's the only way I can go through those points and get to those intercepts and get to that horizontal asymptote. So it's got to be one of those two. Let's do some calculus to figure out which one it is. Which means I need to find my derivative to look for critical points. So I'm looking at a quotient rule. Oh, Joy, question?
Why is there 2 lines in it?
Well, I don't know which one it is without doing calculus. So this is not my real graph. This is my in the meantime graph. I'm just saying if I ran out of time, I would pick one of those and sketch it and hope for partial credit, right? Because I know the 2 points I have to go through, and I know I've got to get to that horizontal asymptote. So I'm just going to put something plausible down on the paper in case I run out of time. Now, for my derivative of the top is 1, leave the bottom alone, minus, leave the top alone, times the derivative of the bottom is 2x. And then the whole denominator is getting squared. Now, I already know based on the picture that I am expecting to have a relative minimum and a relative maximum. So I'm hoping that the top is quadratic and factors. If it doesn't factor, we're going to use quadratic formula, but let's see where we get. So in the numerator, I've got x squared plus 9. And now I'm distributing all of this stuff out. So 2x times x, it's going to give me a -2x squared. 2x times -1 would give me a -2x, but I got another negative, so plus 2x. So in the numerator, that's not going to factor, is it? That's really unpleasant. in the numerator, I am looking at 9 minus x squared plus 2x. And if I set that equal to 0, in terms of looking for those critical numbers or the critical values that are going to break up that number line, the bottom is never 0, so it's not contributing anything. Joy, please tell me I made a mistake and it's going to factor.
I want to ask, can we not like, because this is first x plus 9, separate them?
She means like x squared plus 3 squared. What the?
Well, the issue is that I've got this other negative 2x squared. So like sometimes you might get lucky and it's going to factor by grouping. This doesn't look like it's going to factor by grouping. Yeah. I mean, good to look for it to see if there's a way to factor by grouping, but I don't think it's going to happen here. So instead, I'm going to rewrite that so that it's kind of in the order that we usually write things in if we're going to do quadratic formula. Looking at negative b, so negative 2 plus or minus the square root b squared, so 2 squared is 4, minus 4 times a times c all over 2a. Underneath that square root, I am looking at, so 9 times 4 is 36, plus a 4 is going to give me 40. So I've got negative 2 plus or minus the square root of 40 over negative 2. Now, if this were like a web work homework, I would not bother to simplify that. But I have to do something with that on a graph. So I'm gonna need to make that a little nicer for myself. And when I look at the square root of 40, I know that that's 4 times 10. Not a whole lot better, but I can look at the square root of 4. And then either break that into 2 fractions or factor out the 2, however you want to look at that. But if I leave that as negative 2 over negative 2, plus or minus 2 over negative 2, square root of 10, I've got 1 plus or minus the square root of 10.
Is it just 1 plus square root?
You could write that as 1 minus plus. That is often how we write it when we have a negative there, but that's kind of a mathy thing to do. We don't really need to do that. Yeah. So in terms of the number line, oh, by the way, now I know which one it is. Is it orange or purple? Oh, sorry. Which of my curves was right? This one or this one? We don't get a calculator on the test, but we've got skills anyway. The square root of 10 is bigger than what? It's bigger than 3. So if the square root of 10 is bigger than 3, then 1 minus 3 is definitely over here. It's not between 0 and 1. So orange curve was right, which was my first instinct. So that means if my orange curve was right, I already know what my number line should look like for the derivative, and I already know what my number line should look like for the second derivative. But I'm going to do them anyway. And I'm going to have 1 minus the square root of 10 and 1 plus the square root of 10. just as a tip, anytime you're pulling things from quadratic formula for your number line, the thing that's like in front of the plus or minus is always in between the two. So I know that x equals 1 is a test point that would be in between these two. And then if you're not sure what to pick, just make the square root of 10 even bigger than it was, right? So rather than thinking about it as a 3, think about it as a 4. So 1 plus 4, I know that 5 should be out there. 1 minus 4, I know -3 should be over here in terms of picking test points. Now, one advantage of knowing what our graph looks like is that I actually already know that I need to be decreasing, increasing, decreasing. But if you weren't sure about that, we can plug numbers in. And remember that what you're plugging these numbers into is our f prime. Also, just saving yourself time, the bottom is squared, so it's always positive. So you really only have to look at the sign in the numerator when you're plugging the numbers in. So if I were to plug in 1, I'd have 9 minus 1 plus 2, that's positive. If I plugged in 5, I'd have 9 minus 25 plus 10, that's negative. If I plugged in -3, I'd have 9 minus 9 minus 6, which would again be negative. So my graph should be going down, going up, going down, which matches over here. In terms of the concavity, I can already tell that I should have an inflection point here, an inflection point somewhere in the middle, and an inflection point over here. So I'm expecting 3 points of inflection. Which is really unfortunate because I don't know how to well, there are techniques for factoring cubics, but they're not ones that I would come up with while taking an exam. And if there are 3 points of inflection, I know this next thing is going to be a cubic. So for me, having the graph is what would save me. But did we have to find the concavity on this one? We did. Cool. Okay. So I'm probably going to mess this up when I copy it to the next page. But we've got 9 for our first derivative. We've got 9 minus x squared plus 2x. Yes. Plus 2x. And the whole thing over x squared plus 9 squared. Okay. So if I need to find the second derivative, got another quotient rule going on. Derivative of the top looks like -2x plus 2. Leave the bottom alone. Leave the top alone. Times the derivative of the bottom. And when I take the derivative of the bottom, I need a chain rule. So I'll bring my 2 down from the exponent, leaving me with an exponent of 1. And then I'll multiply by 2x because that's what was on the inside. And that whole thing would be over x squared plus 9 squared, meaning it'll be to the 4th. So if I set this equal to 0, I am not multiplying everything out. I am looking for anything at all that I might be able to factor before I try to multiply stuff out. So this and this tell me I can at least factor out an x squared plus 9. If I factor out an x squared plus 9, I would be left with from the first piece, negative 2x plus 2 times x squared plus 9. From the second piece, I would be left with 9 minus x squared plus 2x. I'm going to take that 2 and that 2x and multiply them together to get a 4x. And that whole thing is over x squared plus 9 to the 4th. One of these will cancel out. That's going to be a cubic, which if we get really, really lucky is going to factor. Have you all seen the solutions? Is it going to factor?
Oh.
Oh, that's okay. Do we want to keep going?
I mean, if we have this on the test, which
So honestly, if you have this on the test, once you have your first derivative, you kind of know what the graph looks like. I knew what the graph looked like before the first derivative. But once you got your first derivative, you kind of know where we're going up and down. So if you know where you're going up and down, this is my practical advice for the test. I'm just going to draw my second derivative down here, and I'm going to go, cool, that was concave down. That's concave up. That's concave down. That's concave up.
why is the end concave up? Aren't we getting close to?
We are, but it's still concave up over there. It's like really, really subtle. So, right, but if it's going towards that asymptote, it's got to be concave up over there. So that is my genuine practical advice for the exam is after you get your first derivative, don't wait, just graph it. Move on, do more problems. If for some reason you got extra time at the end of the exam, okay, come back. Now, taking the second derivative, fine. Take the second derivative, but I'm not going to try to solve that. I'm not going to try to solve this on an exam. I might waste 10 minutes trying to do algebra on that. That's 10 minutes where I could have gotten most of the partial credit on a different question. So that's just my partial credit is about collecting points. Collect the points on the problem where you can. This I don't think is worth spending the time to collect the points.
Yeah. This is a general question. I already asked about it before, but I just
That's
wanted to
okay.
be sure.
Yeah.
To find like the relative min and max, you're saying that we plugged it into the original equation, but there has been other problems where they plug it into the first derivative.
So if it's a max or a min, what should you get every single time if you plug that into the first derivative? Let me ask it backwards. How do you find a max or a min? You set the derivative equal to. So if you plug the number back into the derivative, what are you going to get? So I think what you're thinking of is actually the second derivative test. Yeah. And I think what you're thinking of is that if my second derivative, I'm just picking a point, let's say 3 is a critical point. So f prime of 3 was equal to 0. If I plug 3 into the second derivative, and that's negative, then I know that my graph was concave down, and that's a max. If I plug 3 into the second derivative and I got something positive, then I know it was concave up and it's a min. So it's not helping you to find the value, but that is a technique to decide if it's a max or a min.
So basically, you only do plugging into the derivative for the second in order to find the concavity and the inflection.
Yeah. Yep.
This technique we use when doing optimization.
You can use the number line technique when you're doing an optimization
Yeah.
problem, but this is easier.
Second.
Yeah, this is generally easier for an optimization problem if you're gonna show that it's a max or a min. But again, this doesn't give you the max or the min. The max or the min you're getting from plugging it into the original function. This is just telling you whether it is a maximum or a minimum.
Also, I mean, it's fine if you don't, but will there be any answers for these?
Yeah, I did not get a chance to write them this morning, but I will definitely post solutions to this. And there are solutions to the other two practice exams that I put in Canvas. Yeah. Yep,
Do you think they'll talk about the number 12?
probably. I have plenty of time. Let me just check and see if anyone has reserved this room after me. Let's see. I think I can pull that up on my phone.
Also, do you have any like rate problems? Because I feel like that is probably gonna be on the exam.
There are definitely related rate problems. So 6A is a related rates problem on these practice problems. But I have more in Canvas for sure.
Isn't number 12 related with numbers?
Probably. Yep, 12 is also a related rates problem.
I bet, because I thought related rates problem was just like when you do like or like the temperature of the room.
So those are not related rates problems. Those fall under the category of exponential growth and decay. So sometimes they're called decay rate problems. I know, unfortunately, right. Someone could choose some better wording on all of this. They kind of all start to sound the same. So finally got the room calendar open, and there might be like a chemistry review in here. Okay, we can have the room till 2. Someone else is in here till 2. So, or someone else is in here at 2. So I'm good. Let's keep going. Which was the one that, which one did you ask about, Joy? 12? Oh, the related rates problem. Okay. Okay. So the water in a cone-shaped tank is running out of the bottom of the cone at a rate of 2 cubic feet per minute. How fast is the water level changing when the water in the tank is 8 feet deep? The tank has a radius of 5 feet and is 12 feet high. And I've given us the equation for the volume of the cone. Okay. If you encounter a word problem, it is kind of important to be able to tell what kind of word problem it is, so I know what I should be doing. Blah, 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 word, how fast? If I am being asked a how fast question, I know that's some kind of derivative. Now, to your point about how fast could show up in wording in an exponential growth and decay problem. So let's look for more clues. Really? The clue that I am 100% sure I'm doing a related rates problem is that I've got units that are per unit time. If I've got something that says per second, per minute, per hour, per day, if I've got something happening per second, per minute, per hour, per day, right? I've been asked to how fast, all signs point to this is a related rates problem. If it's a related rates problem, I'm following the same steps each time. That first step is to write down any of the rates. Now, in this case, I see a 2 cubic feet per minute. Now, if it's cubic feet, those are units of what? So I know that that is the dV/dt. Now there's a subtlety in this question because the water is running out of the cone, which means that rate should really be negative. If you missed that, I think you'd still get most of the points in the problem. Now the other rate is whatever the how fast question was. So it says how fast is the water level changing? So I'm going to choose to rate that as dW dt and just put a question mark in there because we're looking for that how fast. And I don't see any other rates. There aren't any other things that have units of per minute. So once I've got my rates, the next step is to write an equation. And for me, this step often requires a picture. I was nice. I gave us an equation for the volume of a cone. There's just one problem with the equation I gave us. It has an R and an H in it. And I don't know anything about rates for R and H. And it doesn't have a W. And that's what I was looking for in the first place. So I'm going to need a picture. In my head, this cone has the tip down, but there is nothing about this problem that tells you to put the tip at the bottom. How did you all envision this cone? Tip down or tip at the top? Down? Okay, we'll take it as down. That's how I was thinking about it too. So I'm going to draw this cone in, not very well. I don't draw well in 3D, but it's good enough. Okay. So here's the cone. I'm going to just sort of flatten that to be a two-dimensional shape for myself so that I don't go crazy trying to draw in 3 dimensions. But it once was full, but there's water in there, right? And now there's like a water level somewhere and it's dripping out. Which means that there's a water level here. And my W is really referring to that water level. The overall cone itself has a radius of 5 feet and a height of 20 feet. In terms of that volume equation, what is changing is not the volume of the cone, it's a tank. It's not like shrinking. What's changing is the volume of the water. So I've got to take that volume equation and make it about the water in the tank. So here's my water level for the tank. That's the radius of the water. So my volume would look like 1/3 pi r squared W. But I still have a problem because I don't have a rate for R. So I'm going to need to use similar triangles to get rid of R in this equation. So here in terms of my triangles, I know that 5/20. So this side to this side for my big triangle would look like R/W for my small triangle. So R would be equal to 1/4 W. Right? 5/20, that's 1/4, yeah. And my volume equation for the water would then be 1/3 pi times 1/4 of W squared times a W. And I would recommend before we move on to step 3, which is to take a derivative, that we try to clean that up a little bit at least. Clean up the numbers and stuff. So 1/4 squared, that's a fourth times a fourth. So that's 1/16. 16 times 3 is 48. So I've got pi over 48. W squared times another W is W cubed. Third step for a related rates problem, I need to take the derivative with respect to time. When I do that on the left-hand side, that looks like just writing dv dt. When I do that on the right-hand side, I actually have to take the derivative. So I'll have 3 pi over 48 times W squared. And then because it's with respect to time, I've got to remember to multiply by dw dt. The last step for any related rates problem, and I've been getting this question a lot in drop-in, it is important that you not plug in values until the end. If you plug them in before the end, derivatives have a tendency to go to 0. So the last step is to plug in the when. And in this case, it's when the water in the tank is 8 feet. So I know the dv dt is -2. I know that I'm going to plug in 8 for W, and you can simplify the numbers or not, but we need to rearrange to get dw dt. Yes, you can simplify the numbers. Maybe it's worth your time, maybe it's not. More questions? Yeah.
Could we do number 11?
Yeah. So number 11 on my practice says that we're looking for the largest value of x squared y given x and y are positive, and also that x plus y is equal to 30. So this is an optimization problem because I've been asked to find the largest value of something. And I've been looking at the largest of something, then I'm just going to call this like f equals x squared y. And then look at that and say, oh, I know how to find a max or a min. I take the derivative, I set it equal to 0. But I can't do that because I've got an x and a y in it. Oh darn. I sure hope we know something else. Oh, look, we do. So that other thing that we know, that x plus y has to equal 30, I could rearrange to say y equals 30 minus x. Which means that my function, just as a function of x, would be x squared times 30 minus x. Now I know how to find a max or a min. We take a derivative, we set it equal to 0. I'm gonna do algebra first so that I can avoid a product rule. So I would write this as 30x squared minus x cubed. So when I take that derivative, I would get 60x minus 3x squared. And when I set that equal to 0, it looks like I can pull out a 3x and be left with 20 minus x. So I could have the x equals 0 or the x equals 20. But I already know that x equals 0 is a terrible choice because I was looking for the largest value of x squared times y. And I'm going to get 0 if x is 0. So that's a poor choice. It's probably 20, but for completeness, we could use the second derivative test to show that x equals 20 is the maximum. So if I want to show that 20 is the maximum, I could take that second derivative, 60 minus 6x, and show the f double prime of 20 is less than 0. So x equals 20 is our max. But if the question is for the largest value of x squared y, then my final answer is going to be, oh, sorry, I don't know why I wrote x equals 0. I think I said 20 and wrote 0. It's all good. Equals 20 is our max because this was concave down. If x is 20, then I know y is 30 minus 20 or 10. And I know that my max value of x squared y would be 20 squared times 10 or 4,000. More questions?
This problem.
Sure.
You can start over here if you don't want to.
Oh, I don't mind, but, oh wait, just the first one, the
yeah.
fifth root of a sub n?
Mhm.
Okay. So a sub n plus 1 is equal to the fifth root of a sub n. And so if I'm going to classify, so we're looking for the equilibria and then classifying them. So find and classify the equilibria. And so this gets back to that idea of the stability criterion. So when we go to classify, that's where we're looking for the derivative at our point. What is it relative to 1? So to find the equilibria, again, I'm going to set the finding part. I set a sub n equal to a and a sub n plus 1 equal to a. So I would have a is equal to the fifth root of a. All kinds of options there, but I'm going to just raise both sides to the fifth power and have a to the fifth is equal to a. So a to the fifth minus a is equal to 0. And if I factor that, And I keep factoring that. And I keep factoring that. I'm going to get that my three possible equilibria are 0, 1, and -1. By the way, -1 is still viable because I'm taking the fifth root. So the fifth root of -1 is defined. So I am going to want to check all of them. Yeah.
Are you gonna do all of those 3 A's again? 0, 1.
So 0, 1, -1, this has no solution. Yeah. So when I go to take my derivative, so I'm going to write this as f of x is equal to x to the 1/5. So f prime of x is 1/5 x to the -4/5. Those all look like they're going to be stable to me. So if I look at f prime of 0, oh, 0 is a problem. If I look at f prime of 0, I would have 1/5. That x to the -4/5 tells me it's really in the denominator because of the negative. So if I try to put a 0 down here in the denominator, it's undefined, which means it fails the stability criterion, but I know that that means we're unstable because the only way we're stable is if this is less than 1. If I look at f prime of 1, I've got 1/5. 1 raised to any power is 1. So f prime of 1 is just 1/5, which is less than 1, so we're stable. F prime of -1 would look like 1/5 times -1, but that absolute value is still less than 1, so this is also stable. So 1 and -1 are both stable equilibria, and 0 is an unstable equilibrium. Got 10 more minutes. Anyone have another?
How did you go from square root, or sorry, a to the power of 1/5 to the next one?
So
On the other
over
side.
here.
Yeah.
Okay.
Where did you go?
So if I factor an a out, then I'm left with a to the 4th minus 1.
Like the first 2 lines?
Oh, like here to
Yeah,
here?
yeah.
Got it. So I multiplied both sides, or I raised both sides to the 5th power. Kind of like if you're undoing a square root, you square both sides. If I'm undoing a 5th root, I to the 5 both sides. We're gonna have a cool phrase for that.
Yeah, that makes sense.
Yeah, quint both sides. I don't know. I've like never heard.
I was like confused. I was like, should I square or
Yeah.
lines or-
Yeah.
So if you get a problem like this, you just have to basically.
I mean, unless you put something on that you have to use quadratic formula, but yeah, I mean, the book problems all pretty much factor. Yeah,
Can you do number 10, please?
sure. 10 on mine? Yeah. Oh, and I'm gonna request to do 13. I'm actually, since we're kind of in this mode, let's look at 13 real quick, look at some sequences, and then I'll come back to number 10. 13 will be quick. So if my sequence is defined, oops, that's a -1, and -1. If my sequence is defined sort of as a function-ish and not with an a sub n and a sub n plus 1, then finding the limit is literally just us taking the limit as n approaches infinity. Now, I have made this messy. But if we plug in infinity, we have infinity over infinity, which at this moment might lead you to think using L'Hopital's. It won't help. Don't go there. We have an exponential function on the top and an exponential function on the bottom. So if I have exponential functions, I really want to try to do algebra and work with exponential stuff before I try L'Hopital's. In the section on sequences in our book, there's kind of an important piece to geometric sequences that I think a lot of people glossed over. But if I have something, if my a sub n looks like some number raised to the n, if that number is less than 1, then the limit as n approaches infinity of a sub n is equal to 0. Now, that was kind of a fancy way of saying, if I have something that looks like 1/2 to the n, so I've got eventually like a half times a half times a half times, if I'm taking half of something each time, eventually I got nothing left. But if I have something that looks like 3 to the n, then 3 times 3 times 3 times, if I do that forever, that's going to infinity. So the trick to a problem that looks like this is to rewrite it somehow so that it looks like one of these two forms. So that we're either going to 0 or going to infinity. And the way that I would do it for my particular problem is I would take that 5 to the n minus 1 and write that as 5 to the n over 5 because of that -1 part. And in the denominator, I would write that as 3 squared to the n. So if I clean those up, then on the top, I might think about that as saying like 1/5 of 5 to the n. And that would look like 1 plus 9 to the n. I could maybe just say, I know that's going to 0 because the bottom's going to infinity faster than the top. But if I wanted to rely on this geometric sequence thing, then I would take every single term and divide by 9 to the n. So I would have the limit as n approaches infinity of 1/5 of 5/9 to the n over 1 over 9 to the n plus 1. And that is 0 plus 0, 0 over 0 plus 1. That's going to 0.
At the numerator, did we divide by 9?
I divided by 9 raised to the n. I just stuck it together with my 5. Because if I have 5 to the n divided by 9 to the n, that's the same as 5/9 to the n. And that's really the trick to that question. B, you can just straight up use L'Hopital's. B is infinity over infinity, but everything is powers. And so it's not an exponential function, and you can just use L'Hopital's.
And why did we divide by 9?
So this is kind of like, well, let me look at and make an analogy back to what we would have done at the beginning of the quarter. So before we knew about L'Hopital's, if I had to take the limit as n approaches infinity of n cubed over n squared minus 3n, I would find the largest power in the denominator and either factor it out or divide every term by it. And if I divide every term by n squared, and then simplify each piece, then I can take the limit because I have this piece that I know is going to 0. So dividing by 9 to the n is the analogy to doing this. We're dividing by kind of the largest thing that was in the denominator. I said I would do number 10, so let's look at number 10.
Sir, can I get mass back in the other one?
Sure. So number 10, we're finding the equation of the line tangent to this graph. We've been given a point. So anytime I'm looking for a tangent line at a point, I'm definitely going to get my partial credit first. So I am looking at y minus 0 is equal to m times x minus 1. And I'm just going to write m is equal to dy dx at 1 comma 0.
Martinez is using mx plus b instead of that.
Doesn't matter. Because I'm going to go to mx plus b in the end. But I'm never going to start with mx plus b because it's always more work in calculus. I'm going to get there in the end, but it's easier to do it after the fact, especially if I've got a 0, because this is y equals mx plus b already, once I know my slope.
What's our b then?
Once I know my slope, it's going to be that times -1. We're just going to distribute it out.
Okay.
Yeah. So this is almost always the easier starting point for calculus because of how the questions get phrased. We almost never are told what the intercept is. So if I have to do algebra to find the intercept, I would rather start here and do my algebra just manipulating this equation. So now I actually have to find the derivative. So x minus y, try to copy this down correctly, plus 1 equals 2x e to the y. I'll also say that even if Martinez is using y equals mx plus b, I can pretty much guarantee that the TA who's actually grading your paper did it like this. Okay, so taking the derivative, it's going to be implicit because I've got x's and y's mixed up together. Derivative of x is 1. This derivative I'm going to write as dy dx. Derivative of 1 is 0. Now I've got a product rule. Derivative of 2x is 2. And I leave the e to the y alone. Plus, I leave the 2x alone. The derivative of e to the y is e to the y times dy dx. You could solve for dy dx right now, but I wouldn't because we were given a point. And I know that x equals 1 and y equals 0. And I'm going to go ahead and plug those in because it's going to make it easier. So I've got 1 minus dy dx. E to the 0 is 1. 2 times 1 is 2. E to the 0 is 1. Dy dx. So I know that if I subtract 2 from both sides and then add a dy dx to the other side, that dy dx is equal to -1/3. And I'm gonna put that into our equation. So y minus 0 equals -1/3 x minus 1. There's my mx plus b.
So you can plug it in earlier, you don't have to find it.
Correct. If the question did not tell you that, like, if it's a 12-part question and part A asked you to find dy dx and then part B asked you for the equation of the tangent line, then you'd have to do the